Hello, and welcome back to the channel. My name is Luca. I am a chemistry tutor at Cornell University, and this is my second video. So this will be the second video in this little series that I'm doing on periodic trends, where I try to demystify and help you understand some of the more difficult topics in college chemistry, although this applies to high school chemistry as well. So originally, this whole topic would be one video, but after making this presentation, I decided to split things up as it would be a little too long in one video. So today, we'll be going over the key points that we talked about last time in our primer and talking about atomic radius, which is the easiest to understand, I feel, of the atomic trends, and it will help you understand the other two much more easily. So let's get started. So, in case you didn't see the previous video, the first key thing to refresh yourself on is the Bohr model of the atom. And specifically for our purposes, that each period of the periodic table corresponds roughly to each electron energy level or shell, and I'll use both terms interchangeably, as you can see here. So first period corresponds to this first inner circle, second period corresponds to this second outer electron shell. Okay, pretty good so far. And we're going to skip over this next part that I made on electron configuration, though it'll become relevant when we come back to do ionization energy next time. So, interatomic radius. The first thing to clarify here is that the term periodic trend refers to a property of the elements of the table that changes as we move across the periodic table. So, since atomic radius describes the size of an atom, we'll focus here on how the sizes of atoms change going up and down the table as well as left and right. And then we can integrate those both at the end. So first, we'll talk about up and down the periods. This is a little simpler and easier to visualize. So as we saw a second ago, moving down a period adds a new energy level or a new shell of electrons. So you see here that as we go down from helium to neon to argon, we add a shell in our Bohr model drawing each time. The second main fact here is that new energy shells are higher in energy and therefore further from the nucleus, which comports with what you would just guess from looking at the diagram, right? Like argon's outer shell looks to be further from the nucleus than helium's inner shell or outer shell as well, right? And then putting these two facts together, the conclusion that we can draw is that in this case, argon is bigger than neon, which is bigger than helium, because the outer electron shells are further away from the nucleus. And we derive a consistent rule, which states that the atomic radius increases as we go down the periodic table, so down the periods of the table. And this just makes sense, right? If we add more of these electron shells that get further and further from the nucleus each time, the radius should be increasing. So a little more complicated is when we go across the table from left to right. So for instance, and we'll use this example throughout, going from the sixth element, carbon, to the seventh element, nitrogen. If you don't already, I would get out a periodic table at this point, or you can head over to ptable.com, which I've found is the best online resource for the periodic table. So transitioning from carbon to nitrogen is very different from helium to neon, because instead of adding an entire shell of new electrons, we're just going to add one electron and one proton to go along with it. And you can probably guess why this is more complicated than going up and down the table, because just upon visual inspection, the atoms look to be roughly the same size. So how do we use this up? There are two factors to consider here. The first of which is the effect of adding an electron. You probably know that two of the same charge, so in this case, two negative charges on electrons, will repel. And this repulsion makes the atom bigger than it would be without repulsion, like I'm trying to show here in this top drawing. If there was no repulsion between the electrons, like I show in this inner circle here, they'd be able to get a lot closer to each other, but in the real world, they repel, causing the electron shells to be pushed outwards, like I show with this dotted line here. And this matters for our comparison between carbon and nitrogen because nitrogen has one additional electron when compared to carbon, meaning that there will be a greater number of these electron-electron repulsions. And as you would guess, this has the effect of slightly increasing the radius of nitrogen relative to carbon. So just to fill this in, and this is not a correct diagram, but it's relatively correct, where this carbon appears to have 4 repulsions, where the N appears to have 5 repulsions. So that's one way you can think of it. But we're not done yet, because we also have to consider the opposite effect, which is that of proton-electron attraction, because they're oppositely charged. So when protons and electrons attract, it has the effect of pulling the outer shell of electrons closer in towards the nucleus. It's almost as though you have one of those grip trainer things where the more protons and electrons you have, the stronger your grip would be, and the closer you can bring together those two handles. In any case, we know that nitrogen has 1 more proton and 1 more electron than carbon, meaning it'll have, in our analogy, a stronger grip, which pulls the outer shell of electrons towards the nucleus and makes it a little bit smaller. And if you've taken physics, you will probably think of this as Coulomb's law, where the stronger the charges, the greater the attractive or repulsive electric force between 2 charged particles. Interestingly here, we have 1 force, the repulsion, that makes the nitrogen bigger, and 1 force, the attraction, that makes it smaller. So the real question here is which force matters more? Now, I could just tell you that the proton-electron attraction is more powerful than the electron-electron repulsion, which is correct, by the way. But I prefer to think of it, at least for learning's sake, in terms of a scale. So while this repulsive effect is only created by the new electron that we added when we went from carbon to nitrogen, the attractive effect between them is created by the new proton and the new electron working together, which makes the attraction stronger than the repulsion. It's as though you wrote a musical piece for 1 instrument versus 2. I would guess that the piece written for 2 instruments would be better, more complex. You get the idea. So we can conclude here that nitrogen is smaller than carbon, despite having more protons and electrons. And we can derive the rule that atomic radius decreases going right on the periodic table, or conversely, it'll increase going left on the periodic table. And if we put both these 2 rules together for radius, we will see that the smallest atoms are found at the top right of the table, whereas the largest will be found on the bottom left. So to wrap up here, let's talk through, 4 quick examples and 1 slightly trickier example. So first, which of these 3, rubidium, cesium, and francium, is the biggest? Well, here all we have to apply is our first rule, because we're just going up and down. And we know from that rule that atomic radius increases as we go down the periods, because we're adding shells. So francium should be the biggest in this group, and rubidium the smallest. Now, the next example is rule 2, the one we just derived, where we know that carbon will be the largest because it's furthest to the left, and oxygen will be the smallest because it's furthest to the right. Pretty simple so far. Now, in example 3, we need to consider how the 2 rules interact. So based on rule 1, which again was going up and down, arsenic should be smaller than indium because it's further up on the table. Pretty simple. And therefore, it has 1 less shell of electrons, which is a lot. And if we apply rule 2, the left and right rule, we get the same result, where arsenic should be smaller because it's further to the right on the table. And in this case, both rules agree that arsenic is smaller, so we can say with a lot of confidence that arsenic is indeed smaller. And if you look it up, you will find the same thing. Now, example 4 is a bit trickier. So in this case, rule 1 would suggest that boron is smaller because it's way further up on the table and has 5 fewer electron shells than this UUP atom, which I believe now has a name. Upon checking, it is now called muscovium, but I guess my table's a little outdated. So based on rule 1, boron's smaller. However, rule 2 would tell us that the atom to the right is smaller, which would suggest that muscovium, or UUP, is smaller. So which one's right? Which rule takes priority here? And I'd say in this case, it's pretty obvious if we apply a little bit of common sense. So while muscovium, or UUP, does have more protons to pull those electrons in, like that grip strength we talked about, it has so many more electron shells than boron that boron just must be smaller. And if we sketch a Bohr model of these two and compare them, I think it becomes increasingly obvious, where boron has 2 little electron shells, and maybe they're a little bit far apart like this, where moscovium has 7. So let's draw those. 1, 2, 3, 4, 5, 6, 7. And you can see that no matter how much I try to squish these little electron shells in, moscovium is still pretty clearly bigger than boron. And we'll see that as well if we check on a periodic table. So boron's smaller here. Now, example 5 is not so simple, even though it appears to be the same scenario. So while antimony does have an additional electron shell, it only has 1 more shell than gallium. And it's also 2 places to the right of gallium. So in this case, again, rule 1 says gallium is smaller, but rule 2 says antimony is smaller. Now, in this case, where the atoms are very close together, it's hard to figure out which rule should be more important. And the nice thing here is that you actually won't be expected to know which one is larger or smaller because they're so close together and it's hard to determine which rule takes priority. So if this were an exam, you could just put down that it is not possible to determine which is larger or smaller given the information, and you would still get full credit. That's totally fine. So that ends this video today on atomic radius, and check back next time for an in-depth look at ionization energy, and I will talk to you then.